Okay, we've been talking about finding rate of change functions. So what did we do? So the whole mastery exam was about, given a function, y is a function of x, did we have some shortcuts for writing out the rate of change function, y as a function, or the rate of change of y with respect to x. And then we saw that if you have an equation where y and x are kind of like intertwined, right? We could also find the rate of change. We'd still find the rate of change of y with respect to x, even though y wasn't a function of x. And how are we able to do that? Roman?
Through implicit differentiation?
Yeah, that's implicit differentiation, where we kind of like, instead of solving for y first, we just differentiate each term, term by term, with respect to x, and then isolate y prime. So we're solving for the rate of change with respect to x, even though y isn't a function of x. So the next thing is something called related rates. So what does this imply? It implies that there's not just one rate of change, but more than one rate of change. And how are they related? So mathematically, can we, in a given situation, can we come up with an expression or equation that's bringing together more than one rate in the same situation? Okay? So let's, so this was the ladder problem that we looked at Monday. And we said that the quantities x and y were always in this relationship, according to the Pythagorean theorem, even as the ladder fell, right? Even as the ladder fell, the hypotenuse stayed at 10. That was the length of the ladder. And as x increased and y decreased, it still maintained this relationship for any given point where the ladder is falling. So we worked through and we got a rate of change of y with respect to x for that falling ladder. So that was the rate of change of the top of the ladder with respect to how the bottom of the ladder would move. Okay? So given a small change in the bottom of the ladder, this would tell us how fast the top of the ladder was moving down. Okay? Okay, so now let's suppose that we're going to bring time into it. So now the bottom of the ladder moving away from the wall, we could think of as a function of time. Like we could start the clock when the monkey kicks the bottom of the ladder, right? And we could time the the bottom of that ladder going across and the top of the ladder coming down. So therefore, we said that the bottom of the ladder was moving at a constant rate across, right? So whatever the velocity of the ladder is, to get the x position, then you would take that velocity times the amount of time. So therefore, the rate of change of the bottom of the ladder with respect to time, so in other words, so this is like saying dx dt. Right, so dx dt we can write as x prime t, those are the same thing. It would be that constant rate, whatever the constant rate is of the bottom of the ladder moving across, that would be the velocity. And we could label that dx dt or x prime. So the relationship between x and y is still the same. X squared plus y squared still equals 100. But what's different about the way we're thinking about this now? So it's the same relationship, but this implies that we're kind of thinking about it differently. How are we thinking about it differently, even though it's the same relationship? Joe?
X is a function of time, and like y is a function of time?
Yeah, so now we're thinking about both of those quantities as functions of time, or after a certain amount of time goes by, it will determine what x and y are. So how would we, so if we want to relate, so we talked about this is dx dt. So what if we want, so now if x is a function of time and y is a function of time, then there are two rates here with respect to time. There's the bottom of the ladder, position of the bottom of the ladder, how it changes with respect to time, and how the top of the ladder changes with respect to time. Okay? So now we want to come up with, how could we come up with an equation that relates those? So the rate of change of, I don't do that. Okay, so the rate of change of the top of the ladder with respect to time would similarly be dy dt. So how could we come up with an equation that now we have these two rates, so that the equation would relate those rates. The equation would have both those rates in them, and therefore be a relationship of those rates. How could we get a relationship of dx dt and dy dt? Any ideas? You, Tom. Idea? It's okay.
Would we just solve it?
Yeah, but these aren't rates, right? This is just position. X, this is an x prime t. This is just the position. This is just x position and y position. So I'm asking, can we come up with an equation that will relate those associated rates, dx dt and dy dt? Will. Okay? Implicitly differentiate this. With respect to what? X? We want to do it with respect to x? If we do it with respect to x, what will we have? The same thing we did before, right? So this is what happens when you go with respect to x. You're kind of ignoring time. So will.
We want to do the same things in that we'll implicitly differentiate them, but we want to get the x parts on one side and y parts on the other. Since now they're both functions.
Right. So yeah. So yeah, we don't really need to move before we take. We don't have to need to move anything before we do. But but yeah, what they both said is right. So we're going to take the derivative with respect to what? Time. Okay? And so that means both sides. But now, so notice you've got x squared, but x is a function of time. And you still got y squared, but y is a function of time. See if you can do the next step. See if you can do this implicit differentiation. So what are we doing? We're doing d of that dt and d100 dt. So the first thing is, how do we take the derivative of a sum? Jack. Right, it's the sum of the derivatives. So we're going to do this one first. dx of t squared dt. Anyone think they got that? Somebody knew. How about Adra? Did you get d of x t squared dt? No? Nathan?
Is it 2x t prime plus
2x.
t prime?
Okay, so think of this. This is just x. It's just x as a function of t. So what will the rate of change be? So it's just, this is really still x squared. It's still x squared. You tell me.
2xt times t prime.
So 2x of t, like to the first, right? So power rule first. But then we've got an interior function of t, so we need to multiply by t prime. Agree with that? It's not t prime.
V prime.
Not v prime.
X
X prime, dx dt, dx dt. It's the derivative of this with respect to t. That's the chain rule, right? Exterior function would be the power rule. Interior function would be the derivative of x with respect to t, or x prime. Does it make sense? Okay, then the derivative of the second one. How about Daniel? 2 times yt times y prime t. You want more than that? That is dy dt. It sounded like you wanted to multiply it by it again. No. Okay. Right. So this is the same. You could write dy dt here or y prime. Okay. Jack, question?
It's for d prime for x prime t.
Uh huh.
Why don't we take the derivative of the inside function of t?
Yeah. So it would be the derivative of t with respect to t. What would that be? It's 1. So we've gotten it down to there's no really more interior function. It's just the variable we're doing. You see? Yeah. You could, but it would just be 1. Okay, what about d of 100 dt? Constants are 0 regardless of what variable you or what quantity you differentiate with respect to. Whether it's x or y or t, there's a constant. It doesn't change as t changes, that's the point. 100 doesn't change as t changes. So it's 0. Okay, so now we need, so because we're differentiating with respect to t and not x, everything has the chain rule now, because x is a function of t and y is a function of t. Okay, so there it is. So depending on the situation, you might want to solve, so you might say you were asking, the question asked you to find how the top of the ladder is changing with respect to time. What would we solve for? So it's asking how fast is the ladder in feet per second, how fast is the ladder traveling downward when x is 5 or something like that. What would you solve for? Jenica? How fast is the top of the ladder falling at a certain time? What would you solve for? Y prime. Is that y prime? How fast the top of the ladder is falling? Yeah. Because y is height of the top of the ladder, and y prime is its rate of change. So both of these are just different forms of the same relationship. They both express the exact same thing. This one just has it solved for y prime. But notice that in both of these equations, we have both y prime and x prime. 2 rates. Now, 2 rates. So that's why this is talking about related rates. So both of these are related rates equation. So here's the important question that's going to really got to keep this in mind when you're solving these problems. If a question is referring to multiple rates and we need to get those related, where is that related rates equation going to come from? What's the source of it? How are we going to where do we start building so that we can get to this equation that relates the rates? What's the source of it? Charles, any idea? Where did we get it? So where did this come from? Did this come from this? Is that where we got it? Yeah, right? So what's the moral is, if we're relating the rates of two quantities, in order to get that equation, we need the equation of the original quantities, how those are related. So to get a related rates equation, we need to start with the related quantities equation. So the quantities x and y, those are the rates that are related, so we need an equation that relates those quantities. And we can use implicit differentiation with respect to t to get the related rates equation. Okay, so here's a problem from the textbook. The edges of a cube increase at a rate of 2 centimeters per second. How fast is the volume changing when the length of each edge is 50? So here's the type of thinking that you got to break out of. You got if you've used this kind of approach in the past, we've got to break the bad habit. You look for the numbers and you ask, what am I going to do with the numbers to get an answer? Okay, that will lead you into a very fast dead end. Okay, so here are the numbers in the problem. What are they asking me for? What can I do with the numbers to get an answer? Okay, it's not going to work. Okay, this is a multi-step process, and the problem gives no indication of how to navigate through to a solution. Okay, so it's what you must do that the problem doesn't ask you to do that makes the problem harder. So if you're just looking for a quick calculation of the numbers involved, it's not going to work out for you. So rather, we want to employ the thinking that we just talked about in that last page, when we talked about the related rates of the ladder. So what did that thinking compose of, or what was it composed of? Identify the specific rates involved. So when you read this problem, it's going to refer to rates of change, more than one. Let's isolate those just as an idea, not as values, but just as ideas. What is one rate that's being, like as a phrase or a statement, what's one rate that's being referred to here in this setup? Saskia. Okay, so volume is a quantity, so say it as a rate. What's the rate that you're talking about? Okay. Yeah, it will. Yeah, so the rate of change of volume with respect to time, because it says how fast is the volume changing? How fast is the volume changing? So the rate of change of volume with respect to time, that's one of the rates. Another rate. Ben, do you see another rate here?
The edges with respect to time?
The rate of change of edge length with respect to time. Okay, so because it's saying the edges of the cube are increasing at a rate of. It's talking about the rate of change of edge length with respect to time. Okay, so how fast the edges are changing, how fast the volume is changing. Those are the two rates that are being referred to in this problem. You see that? That's what you want to focus in on first. When you see these problems that involve more than one rate, identify exactly what those rates are. So rate of change of edge length with respect to time, rate of change of volume with respect to time. And so what's going to be our goal in the end? Our goal in the end is going to be an equation that relates these two rates. And so how is it that we're going to get that equation that relates those two rates? Do you remember what we talked about? Where's that equation going to come from? Kim, remember what we said? The equation that relates the two rates. Where does it come from? Jimin, do you remember? What about the original quantities? Yeah. That's right. Okay. So there's two rates. There are quantities associated with those rates. So let's talk about those first. What are the quantities associated with these two rates? Now, if we really understand those rates, this is the easiest thing. So this is the rate of change of volume with respect to time. What's the associated quantity? Everybody. It's easy. Volume, right? Rate of change, oh, that's this one. Rate of change of edge length with respect to time. What's the associated quantity? That's the unit. Edge length. Edge length is the quantity associated with this rate. Volume is the quantity associated with this rate. And then we also have time. Okay? So let's call the edge length S. We'll call volume V, and we'll call time T. And so, Jimin, you said, what do we need then to get a relationship between those two rates? That's what you said.
The original.
What about the original quantities? Yeah, it's going to be the relationship between these quantities is what we're going to use implicit differentiation to get the relationship between these rates, right? Make sense? So really the focus quantities are this. How fast the edges are changing, associated quantity, edge length, or S. How fast the volume is changing, associated quantity, volume. So we want to write a function or equation that defines how S and V are related. Can we come up with, based on the situation, an equation that relates S and V? Bailey. So, our edge length and volume related. What's that? No, how are they? So yeah, they are. But how? Like what mathematical relationship brings together volume of a cube and side length of a cube? Okay. What is the relationship? Will, it's dying to say. Say it a little louder. So volume equals, is this what you said? Okay. Okay, and you can say you could do, all right, V of t equals S of t cubed. Yeah, good. We also have that S is a function of t, right? What's the relationship that brings together, if you knew what the time was, what the side length was? Yeah, Ben.
50 plus 2t.
50 plus 2t. No, that's not the side length. 50 plus 2t. That would be if t started if t started when it was 50. That's true. So if t was 0 when we started at 50 centimeters, that would be true. But that's not the way we want to set it up. Yeah, actually, that'll work fine if you want to say that. But what were we going to, Patrick?
S of t equals 2t.
Yeah, so actually, either of these are fine. It's just when do you say time is starting? This would be time is starting when the cube is 50. This is saying that time starts when the cube is, nothing, right? It's coming out of nothing, right? So as soon as time starts, we have a cube starting from a point. Really, either one will be okay. Okay, so those are our relationships. The main one being this one. Why? Because what are our rates? S with respect to time, volume with respect to time. So this is the main one because it brings together the associated quantities, volume and side length. Okay, so related. So we're gonna now use the above to relate the rates. So our whole goal was to get a relationship between these two rates. That was the whole point. Where did that come from? It comes from a relationship between the quantities. So can you do it? Can you find the relationship between the rates of volume and side length? See if you can do it. Nick. Doesn't it go by Nick? Do you go by Nick?
Yeah.
Yeah. What do you think? Did you get it? So what are we after here? So we're not looking at the numbers. So notice we haven't looked at any of the numbers yet. We're still making sense of the problem. We need a relationship that brings together the rate of change of edge length with respect to time and rate of change of volume with respect to time. So Ashlyn, did you get it? Okay, you can do that. That's valid. We can do that. Does that, anything else? So we got to get the rates involved, right? So these are just now quantities of volume and time or volume and side length. We got to get the rates involved. How do we get the rates involved? Isabel.
I just left it as BT equals ST cubed, and I did a derivative of that.
Okay, tell me.
I did B prime T equals 3 S of T cubed times S prime T. Yes, squared, does that make sense?
Oh, yes, squared. Okay. Okay, 3s squared.
Times S prime.
How about that? Yeah, so these are the exact rates we wanted. We wanted how volume changes with time and how side length changes with time. And because S is a function of T, we need the chain rule when we do that derivative. Does that make sense to everybody? Yeah, Roman.
For the 3s squared part,
Uh-huh.
how come we don't have to have 3s of t?
It could, yeah, so that it is. Absolutely.
Oh, so we can still have that?
It's just they're both saying the same thing. So this is saying that yes, S is a function of T. But these are the same. Yeah, you're right. This is even better. This is even better. It's more descriptive of what's going on. Other questions? Okay, so there's so many different notations for derivatives. So in my line I chose dv dt, and I chose ds dt rather than b prime and s prime, but they're the same, right? So here's our related rates equation. We related change of volume with respect to time and change of edge length with respect to time. And so from there, so now we have a handle on what's going on. We have a handle of how those rates are related. Now we can go to answer the question. So notice all this stuff that we did was kind of unfolding the situation without even looking at a number yet. Okay? If you jump right to the numbers and just go right for an answer, you're going to miss all this and you're going to miss the problem. Okay, so now can you do it? So how fast is the volume changing when the length of each edge is 50? See if you can solve it. So now we got what we need to answer this question. How fast is the volume changing when the length of each edge is 50? Go, see if you can do it. So Connor, how would you get started on answering that question now?
Would you make all the S's 50?
Okay, so and where are all the S's?
On the right side.
On the right side. So you want to make this 50?
Yeah.
Okay, he wants to put 50 in for this because it's an S value. What about this? Is this 50?
I don't think so, because it's just the rate of change.
It's the rate of change. What is the rate of change of side length? 2. So, 2 ways to look at that. It's given, right? That's given right there. That's the rate of change of edge length. Or, we came up with this relationship with respect to t. What's the rate of change with respect to t? 2. It's the derivative of 2t with respect to t. It's 2. So any way you slice it, it's 2. So we have 3 times 50 times 2 equals, 50 squared. 50 squared, don't forget the square. 3 times 50 squared times 2. What number does that give us? Or what?
Volume. The rate of change of the volume.
Rate of change of the volume.
With respect to time.
And that's what it's asking for. So this was our unknown. In this particular question, that rate of change of volume was the unknown. It told us the edge length. We have the rate of change of edge length. So we got it. Okay, so let me just show you this notation here. So this means this vertical bar like this, it means evaluate this quantity for this condition. Okay, so evaluate this quantity for this condition. So since it wouldn't make sense to do v of 50 because really v is a function of time. So evaluate v when s is 50. That's what that means. And that's what we said, 3 s squared, s of t squared times 2. And s is 50. So how fast the volume is changing every second at that moment, it's increasing 15,000 centimeters cubed per second. Okay. Anybody have a question? So I've really tried to emphasize the ways of thinking that are going to allow you to understand and solve these problems. Here's another one from the book. So a spherical snowball melts at a rate proportional to its surface area. Show that the rate of change of the radius is constant. Okay, so before we get into all the suggestions and advice that I had for you before, let's just flesh out what this means. Proportional, so snowball melts at a rate. Let's kind of make sense of this first statement. Snowball melts at a rate proportional to surface area. So let's just kind of make heads or tails of that, and then we'll attack it in terms of what we've been talking about. So the snowball melts at a rate. What quantity there is implied that's decreasing by that? So melting is decreasing, so what quantity do we assume is decreasing that they're talking about? Will, what do you think? He thinks it's volume. The snowball is melting, that means volume is decreasing. Is that what that means? Right. Okay. So what melts at a rate? So how do we express this, the rate of change of volume? How would we express that? Just V? What would it be?
V prime.
V prime or dV dt, okay? Surface area, let's call it A. So what it's saying is this rate of change of volume is proportional to surface area. So how would we write a relationship mathematically if this quantity is proportional to this quantity? Any ideas? Jerry?
A equal or dV dt equal to A.
Equals A. So if they're proportional, they're equal. Agree with that? Joe?
Wouldn't it be dV dt is equal to some constant A?
Some constant times A. Right. So we have a constant of proportionality. So the rate of change of volume that's what that's saying. Okay? So melts at a rate proportional to surface area. Okay, so before I let you loose on this, let's talk through the kind of the scope of how we're going to think about this. What's the first thing we want to think about or look for in this problem? Remember what we talked about? Jeff, remember what the first thing we want to focus in on is? Okay, that's second. So what before that? Yeah. Yeah, so what rates are involved? Good. So we're gonna write the roadmap out before we do anything. So rates involved. Okay? What will the next thing we do be from there? Jennifer. Okay, don't remember. Crystal. After the rates, we're going to then focus on quantities involved. From there, Sam.
Should you do implicit differentiation?
On what?
On the rates?
On the rates?
Or like the equations for...
So we need an equation, right? So we need to relate the quantities, right? And then what? Yeah, so then we'll do implicit differentiation to relate the rates. Okay, so I'm going to let you loose here for about 5 minutes. But let me just give you a hint. The rate of change of surface area is not in focus here. Do you notice? A spherical snowball melts at a rate proportional to its surface area. Show that the rate of change of the radius is constant. So notice there's no reference to rate of change of surface area. Not part of the problem. So I just don't get off on the wrong track by trying to focus on rate of change of surface area. It's never mentioned. Surface area is mentioned, but not rate of change of surface area. Do you see that? Is that clear? Okay, so go for it. See if you can come up with it. You can work together. Oh. All right, let me give you some things about spheres. Surface area. Anyone remember the surface area? 4 pi r squared. Anybody remember the volume of a sphere? 4/3 pi r cubed. Okay, now you're ready to go. That's a square. Okay. Catch me if you have a question. Come back.
Okay, so it has to be volume. Volume is right.
Identify the rates involved. What associated quantities, relate those quantities. Then go back to all that.
So it's 4 pi
Yeah, that's what we're using, right? So once is r squared, r cubed, r radius. So
And then parentheses. Square root of a divided by 4 pi.
So what are the rates involved? You guys determine that?
Rates are the surface area changes over time.
No, I told you.
Volume changes over time.
Volume changes over time. That's snowball melts, right? Melts at a rate. Okay. What else? What are the rates involved? Change in the radius. So that's gonna dictate how you proceed, right? That's gonna dictate how you proceed.
How do you determine all the
What's that?
How do you determine the rate change?
You don't have to determine it. Just Since it's mentioned, you just note it, right? You're just saying that's involved here. Rate of change of radius. So that's one of your quantities, right? What's your other quantity? What are the rates involved? Rate of change of volume and rate of change of. So what are the quantities? It's so easy. It's like falling out of bed.
Radius and volume.
Volume, right? It's like falling out. This is like the easy. If you get the rates right, this is the easiest thing. It's just like. And so those are the. That's who you want to relate. Relate those two quantities.
Yeah.
Alright, so relate the quantity.
T equals 435
Differentiate.
divided by 25 raised to the
So what it would be like? Guys,
No, there's no R. There's gonna be a
That's not that
yeah. Yeah, that's right.
it's not.
I'm
It's
just
just.
trying to A equal
Are you relating the rates?
to get
No, I'm
to
relating.
get R by itself.
Okay.
I figured it out. So you would
Which A?
you that
Oh, surface area. RT.
Well, the first two questions are
Rate in relation to time.
Well, like,
A radius in relation.
We're trying to find a constant.
Wait.
right?
No.
So
I mean, here's the thing.
Which one? All of them.
The different, like, surface area and volume.
Well, yeah.
There's a third.
Area over DT.
There's 4/3 and
I don't understand
there's 4 in surface area. What? Your face. Yep. Every day.
Wait,
Okay, so then
so we have a
different
So what's the official?
you have that.
just differentiate
Yeah, radius
for
on
what
one
we
side.
have here. 4/3 pi.
And
3
I think that's right. Where we have this other sort of thing, and we have a radius, and so we just solve it. The AT equals. Take the square root of that number. We have to find the rate of change of
Okay, so I've done the first three on the screen. Does it make sense? You follow that?
Yes.
The two rates are volume with respect to time and the rate of change of rate with respect to time. Therefore, the two quantities are volume and radius. Sorry, volume and radius. What equation brings together volume and radius? Our volume of a sphere. Volume equals 4/3 pi r cubed. How do we get the related rates equation? Mary, did you get it?
Implicitly differentiate that equation.
With respect to
Time.
time. Good. Okay, so what will we get on the left?
V prime of t.
V prime of t.
And on the right, 3 r of t t to the second times
Okay.
r prime of t.
Yeah, we got. Don't forget the 4/3 pi. So we'll also have the 4/3 pi in there, right?
Right.
So 4/3 pi times
3
3
r of t to the second
r of t to the second.
times r prime of t.
Awesome. Okay. So now let's simplify this right here. 4/3 pi times 3 is what? This is really 4 pi r squared, right? And we can write rt as, or r prime t, that's fine. So what did we find? We found that dv dt equals 4 pi r squared times r prime of t. So now let's look at what we knew from the beginning. Can we bring those together? What is this right here? That's the surface area. So therefore, what must r prime of t be? The constant of proportionality. You see? This must be the k. Because we knew that dv dt was the surface area times the constant. Well, now we just found that dvt was surface area times the rate of change of the radius. Therefore, that must be the constant of proportionality that we were talking about there. So we just showed that rate of change of time, if this is true, then the rate of change of time with respect, rate of change of radius with respect to time must be constant. Okay. Okay, so for Friday it'll be My Math Lab. Problems like this for My Math Lab. Yeah, you will have a quiz for recitation on Friday.
I'm gonna share them off of math. Yeah, I didn't do it. Dang it. I was so excited. I even cheered Xavier and I was like,
What's up?
Oh, well, you have